Preparing for a characterization engineering interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What is the role of a characterization engineer in the product development lifecycle? A characterization engineer builds confidence that a device performs as designed across voltage, temperature, process, frequency, and load conditions. I develop measurement plans, configure instruments, collect statistically meaningful data, analyze limits and trends, and communicate failures clearly. I also separate design issues from test fixture or process effects. The role bridges engineering disciplines, results guide design improvements, establish operating specifications, support qualification, and eventually improve production test coverage. Strong characterization combines technical rigor, experimental discipline, and concise communication. While answering, explain how characterization connects design, fabrication, validation, and production. Mention measurement planning, corner analysis, data interpretation, design feedback, documentation, and collaboration with circuit, process, test, and reliability teams. Question 2. How would you create a characterization plan for a new semiconductor device? I begin with the product requirements and identify measurable parameters, such as power, timing, accuracy, leakage, noise, and protection limits. Next, I define process, voltage, temperature, frequency, load, and aging corners, then select samples and statistical coverage. I document equipment accuracy, fixtures, calibration, sequence, limits, and recovery procedures. High-risk functions receive early testing and margin analysis. Finally, I automate repeatable measurements, review the plan with design and test teams, and maintain traceable results. Make sure to cover datasheet requirements, performance metrics, operating corners, sample size, test conditions, instrumentation, repeatability, pass criteria, risk-based prioritization, automation, data storage, and schedule dependencies. Question 3. How do you distinguish measurement error from actual device behavior? I first verify calibration status, connections, grounding, probing, fixture integrity, and environmental stability. Then I repeat measurements, compare multiple instruments or setups, and test a known reference device. If the behavior changes with cable routing, range settings, or settling time, the setup is suspect. I also examine repeatability, reproducibility, and an uncertainty budget. Changing one variable at a time helps isolate causes. I only classify a trend as silicon behavior after independent evidence supports it. In your answer, discuss controls, repeated measurements, instrument calibration, fixture characterization, reference standards, probing effects, environmental stability, uncertainty budgets, cross-correlation, and changing one variable at a time. Question 4. What is the difference between accuracy, precision, repeatability, and reproducibility? Accuracy describes closeness to the true or accepted value, while precision describes how tightly measurements cluster. Repeatability is consistency under the same operator, equipment, method, and conditions. Reproducibility measures consistency when those factors change, such as operators, instruments, fixtures, or labs. A calibrated instrument can be precise but inaccurate if it has systematic bias. I evaluate all four through references, repeated trials, gauge studies, and uncertainty analysis before trusting a specification margin. Be sure to define each term clearly and explain how bias, random variation, equipment changes, operators, fixtures, and laboratories affect results, including why precision does not guarantee accuracy. Question 5. How would you characterize a device across process, voltage, and temperature corners? I define the process population using appropriate wafers, lots, or bin information, then sweep supply voltage and temperature within safe limits. I include nominal points and combinations where interactions may create the worst case, rather than testing each factor independently only. Automation controls thermal settling, voltage sequencing, and data capture. I compare distributions, not just averages, and calculate margin against specifications. If a corner fails, I verify the result, isolate the dominant variable, and report both boundary and guardband behavior. Focus on corner definitions, wafer or lot representation, voltage and temperature limits, sample strategy, interaction effects, guard bands, safe operating boundaries, automated sweeps, and identifying worst case rather than only typical performance. Question 6. How do you determine the minimum sample size for a characterization study? I choose sample size based on the decision risk, expected variation, target confidence, and required population coverage. Early engineering studies may use small samples to expose gross issues, while specification setting requires more devices across lots, wafers, and corners. I estimate variance from historical or pilot data and use confidence intervals or power calculations when appropriate. I avoid deleting outliers without root cause analysis. Sample size is a risk decision, not simply a fixed traditional number. Mention variability estimates, confidence and coverage goals, process corners, destructive versus non-destructive testing, statistical power, available lots, outlier treatment, risk, and balancing measurement cost against decision confidence. Question 7. Describe how you would automate a characterization bench. I design the automation in layers: instrument drivers, hardware abstraction, test sequences, data logging, and analysis. Each run records device identity, setup configuration, software version, calibration status, environmental conditions, and timestamps. I add compliance checks, safe power sequencing, settling verification, timeouts, controlled retries, and emergency shutdowns. Raw data remains immutable, while derived results are reproducible through versioned scripts. Automation should reduce operator variation without hiding failures, so every exception is visible and actionable. In your answer, cover instrument drivers, sequencing, configuration management, safety interlocks, settling and timeout logic, retries, metadata, raw data preservation, error handling, calibration checks, and reproducible analysis. Question 8. What steps do you take when a characterization result violates a datasheet specification? I first contain the result and preserve the exact setup, raw data, samples, and software version. I repeat the test with independent checks for calibration, connections, timing, loading, and environmental settling. Then I determine whether the failure is isolated, systematic, corner-specific, or statistically meaningful. I correlate it with design simulations, process data, and other test methods. The corrective action may involve silicon, process, fixture, specification limits, or application guidance, but I never change limits merely to make data pass. Make sure to discuss containment, retesting, setup verification, failure classification, statistical significance, design and process correlation, documentation, escalation, and deciding whether to change silicon, limits, test methods, or customer guidance. Question 9. How would you characterize power consumption for a mixed signal device? I identify every supply domain and define operating modes, transitions, loads, clock settings, and external interfaces. I measure steady-state current and transient behavior with suitable instruments, bandwidth, shunts, or current probes, while minimizing voltage drop and fixture loss. Startup, shutdown, sleep, leakage, and thermal effects receive separate tests. I verify whether reported power includes regulators, I/O activity, or only the device. Results should include conditions, averaging windows, peaks, and uncertainty so comparisons remain meaningful. Cover operating modes, supply domains, steady-state and transient current, measurement bandwidth, voltage drop effects, startup and shutdown, load conditions, temperature, leakage, decoupling, and separating device power from board losses. Question 10. How do you measure and analyze timing performance such as setup, hold, propagation delay, or jitter? I begin by defining the timing metric and reference thresholds precisely, because ambiguous definitions create misleading comparisons. I use controlled stimulus, suitable bandwidth, low loading probes, verified triggering, and adequate sampling depth. For jitter, I separate deterministic contributors from random variation and collect enough cycles for meaningful distributions. I sweep voltage, temperature, frequency, load, and process conditions, then report typical, worst case, and confidence bounds. Setup and hold results require controlled data alignment and careful attention to clock and data paths. Discuss timing definitions, stimulus quality, oscilloscope bandwidth, probe loading, trigger strategy, eye diagrams, statistical distributions, voltage and temperature corners, threshold selection, and separating deterministic from random effects. Question 11. How would you investigate excessive noise or unexpected oscillation in a measurement? I first reproduce the issue and record its frequency, amplitude, operating state, and dependence on load or supply. Then I reduce measurement bandwidth, inspect grounding and shielding, replace probes, verify termination, and test a reference board. I use spectrum analysis or time domain correlation to identify dominant frequencies. Removing peripherals, changing decoupling, and isolating supplies helps separate environmental coupling from circuit instability. I document each controlled change and confirm the suspected mechanism by restoring the original condition. Be sure to mention grounding, shielding, probing, bandwidth, decoupling, loop stability, aliasing, source isolation, spectrum analysis, near-field probing, controlled experiments, and distinguishing environmental noise from circuit-generated noise. Question 12. What is design of experiments, and how would you apply it to characterization? Design of experiments systematically varies multiple factors to reveal main effects and interactions with fewer runs than one factor at a time testing. I define responses and factors, select practical levels, randomize where possible, block nuisance variables such as lot or day, and replicate critical points. A screening design identifies dominant contributors. Response surface methods can then optimize them. I validate the model with residuals and confirmation runs. DOE is especially valuable when voltage, temperature, load, and process interact. Focus on factors, responses, levels, interactions, randomization, blocking, replication, screening versus optimization, statistical significance, and reducing test count without losing insight into dominant effects. Question 13. How do you handle outliers in characterization data? I flag outliers using plots, robust statistics, historical expectations, and physical limits, but I do not remove them automatically. I inspect the raw waveform, instrument logs, device history, operator notes, and environmental record, then retest when possible. If the measurement failed, I document a justified exclusion. If the device genuinely differs, it remains part of the population. I report both the observed distribution and any sensitivity analysis. Outliers often reveal latent reliability, process, or setup problems. In your answer, explain detection methods, physical plausibility, retesting, traceability, measurement fault investigation, robust statistics, exclusion criteria, and why outliers must not be removed solely because they worsen reported performance. Question 14. How would you perform correlation between bench characterization and production test results? I start by testing matched units with equivalent conditions and clearly aligned parameter definitions. I compare distributions, repeatability, offsets, slopes, and failure classifications rather than relying on correlation coefficient alone. Differences may come from timing, loading, temperature, fixture parasitics, or algorithm implementation. I investigate systematic bias and quantify measurement uncertainty before proposing a production limit. A good correlation study demonstrates that the production screen catches relevant risks without excessive false rejects or unnecessary test time. Mention matching devices and conditions, measurement definitions, probe or load differences, linearity, regression, correlation coefficients, systematic offsets, guardbands, repeatability, and converting engineering measurements into robust production screens. Question 15. What are guardbands, and how do you set them responsibly? A guardband is an internal decision margin placed inside the customer or datasheet limit to account for measurement uncertainty and future variation. I set it using uncertainty budgets, process capability, distribution data, test repeatability, and the relative cost of false passes versus false rejects. The margin must be evidence-based, not arbitrarily conservative. I validate it against historical yields and customer risk, document the rationale, and revisit it when the process, equipment, or specification changes. Cover specification limits, measurement uncertainty, process variation, customer risk, false pass and false fail trade-offs, statistical confidence, capability data, and periodic review as equipment or process conditions change. Question 16. How do you characterize reliability-related behavior such as aging, drift, or electromigration? I define the failure metric, initial baseline, stress conditions, duration, sample population, and periodic read points before beginning. Voltage and temperature are selected to accelerate relevant mechanisms without creating unrealistic failure modes. I track degradation trajectories, not only pass or fail, and distinguish reversible drift from permanent damage through recovery checks. I use appropriate models cautiously, report censored samples, and correlate results with physical evidence. Reliability conclusions require clear assumptions, controls, and statistically defensible margins. Make sure to discuss stress conditions, acceleration, sample size, periodic measurements, failure criteria, temperature and voltage dependence, degradation models, censoring, recovery effects, and separating reversible drift from permanent damage. Question 17. How would you validate a new test fixture or probe card before using it for characterization? I inspect mechanical alignment, contact integrity, grounding, shielding, thermal paths, and safe voltage or current limits. Electrically, I measure continuity, contact resistance, parasitics, impedance, and frequency response as relevant. I run calibration standards and stable reference devices repeatedly across operators and days. Results are compared with a qualified fixture to identify offsets or bandwidth limitations. I release the fixture only after repeatability, reproducibility, and correlation meet documented criteria, with maintenance and recalibration intervals defined. Discuss mechanical fit, electrical parasitics, continuity, calibration, contact resistance, thermal behavior, repeatability, reference devices, frequency response, safe limits, and comparing fixture results with an established setup. Question 18. How do you communicate characterization findings to designers and managers? I lead with the conclusion. What passed or failed, under which conditions, with what margin and confidence. I show a small number of clear plots, include sample and test method details, and distinguish measured facts from hypotheses. For failures, I explain customer or schedule impact, likely causes, recommended experiments, owners, and decision dates. I tailor depth to the audience without hiding uncertainty. A strong report enables action, not merely data transfer, and remains traceable for future reviews. Focus on concise problem framing, conditions, evidence, plots, statistical context, impact, confidence, root cause hypotheses, recommended actions, ownership, timelines, and clearly separating facts from assumptions. Question 19. Tell me about a time you had conflicting data from two characterization setups. In one project, two benches reported different gain values for the same devices. I preserved both datasets, compared stimulus levels, bandwidth, loading, calibration, firmware, and fixture paths, then measured a reference standard on each bench. The discrepancy traced to a probe interaction that changed the input impedance at high frequency. We corrected the fixture, updated the method, and added a reference check to every run. Correlation improved substantially, and the documented control prevented recurrence during later characterization. Be sure to structure the response with the situation, technical comparison, controlled experiments, calibration and fixture checks, root cause, corrective action, and measurable improvement in correlation or repeatability. Question 20. What qualities make someone effective as a characterization engineer? An effective characterization engineer is scientifically skeptical, technically hands-on, and disciplined about evidence. I need strong fundamentals in circuits, devices, instrumentation, statistics, and scripting, but also the judgment to recognize when data is suspicious. I define experiments clearly, automate repeatable work, protect raw data, and investigate failures without defensiveness. Communication matters because results influence design and product decisions. The best engineers move quickly while preserving traceability, safety, uncertainty awareness, and respect for cross-functional partners. In your answer, emphasize measurement fundamentals, curiosity, skepticism, statistical reasoning, automation, failure isolation, documentation, safety, cross-functional communication, ownership, and balancing speed with reliable evidence. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.